Hi guys, and welcome to lesson 12. Today we're going to do continuous random variables. So remember that a probability is the map from the subsets of omega to the interval 0 to 1, and a random variable is a function from omega to the real numbers. And whenever we're looking at a continuous random variable or a continuous distribution, we're letting omega equal the real numbers. So a random variable in this case is just a function from R to R, which is the sort of function you're used to dealing with from high school. So these are just real valued functions. For example, like f of x equals x squared or something would be like a random variable in this case. But we use capital X to represent the random variable, and little f of x is going to be the p.d.f of the random variable. And whenever we say f is the p.d.f, that means that the probability that the random variable x is between a and b is the integral from a to b of f of x dx. So remember that for a continuous distribution or a continuous random variable, the probability of getting a particular point is 0. And therefore the probability that x equals a number a is 0, and the probability that x equals a number b is also 0. So inequalities in this case doesn't matter if they say less than or equal to. So the probability that a is less than x is less than b is the same as the probability that a is less than or equal to x and is less than b, and so on. So it actually doesn't matter if you put less than or equal to for a continuous random variable, and so we'll be a little loose with that. And all of these equations will give you the integral from a to b of f of x dx. A couple of notes on the p.d.f f of x. Again, this is representing a probability, so we need values that are always bigger than or equal to 0, because you can't have a negative probability. And the total probability has to be 1. So the integral from negative infinity to infinity of f of x dx equals 1. Recall that if x is a discrete random variable, and we want to find the expected value, we take the sum over x of all possible x's that could come out of x times little p of x, where p is the PMF, the probability mass function. So if we go to the continuous case, we get an analogous equation. So a sum, if you think what happens whenever you go from discrete to continuous, a sum becomes an integral, and then the PMF is going to become the p.d.f. So this is how you define the expected value of a continuous random variable. So we get the integral from negative infinity to infinity of x times f of x dx, which looks very similar to our sum above there of the sum of x times p of x. And the properties end up being very similar as well. So we're going to let x and y be random variables, continuous random variables in this case, and a and b be any constants. Then the expected value is still linear. So the expected value of ax plus b is still a times e of x plus b. And it's also linear over the random variables. So the expected value of x plus y is e of x plus e of y. The variance is still defined the same way. So we take the expected value of the distance from a random variable to its mean squared. And here these expected values represent integrals. So if you look at this closely, I mean, you could substitute in the equations if you like on paper, and you'd notice that this is going to involve a double integral. The variance is still going to satisfy that the other formula that we derived earlier, that it's the e of x squared minus e of x squared formula. So. And it's also nonlinear in the same way that the expected value was, so it's more quadratic. The variance of ax plus b is a squared times the variance of x. Okay, so that's our continuous random variable. It's pretty analogous to the discrete random variable. So I'll see you guys in class.